And welcome back, guys. This is Chris here with a new tutorial series on manufacturing process. Right, this is a tutorial series based off of my previous year's course module with the same name of manufacturing process. And in this tutorial, we'll be creating a 5-spoke chair base. Or more importantly, understanding of injection molding using Solidworks or any CAD software, and using finite element analysis, and creating a 5-spoke chair base that meets these specific requirements on your left. These specific requirements are from my lecturers from the previous years, and if you're from APU and you're my juniors, do say hi in the comment, right? And hopefully this tutorial is able to help you out in understanding and recreation of a 5-spoke chair base that suits you well, right? So before we get started with the requirements and going through requirements and all, let's get to know what we'll be doing for this 6-part series. In this 6-part series, we're going through model making, right? To make the model, 3D CAD modeling using the software Solidworks, right? Creating your chair base, understanding how to choose materials here, choosing mass properties, checking your mass, ensure the mass is correct, right? It's less than 1,000. Ensuring your measurements are correctly using a drawing view, right? Doing a draft analysis check. It's a green ones, positive and negative draft analysis check. A part thickness check to ensure that you have no thin or too thick parts that will cause sinking and flashing during your making of your model, right? During injection molding lah. Understanding the basics of injection molding as well and how it works, right? Going through roughly FEA analysis, how to do FEA analysis, a deep dive down, using mesh refinement, local mesh refinement, right? Understanding, things like elements, understanding pressure, where to put your pressure, right? And then plot all of them into a convergence graph with less than 2%, and to be able to hit your targeted stress level lah, basically. Then we also have to talk about the design choices for 5-spoke chair base and how to create one that is able to fit these specific requirements, which is not easy. I should say not easy, alright? You could see here, I have a lot of variations, 5 variations with 6 revisions. So yeah, not easy, but I will help you out, and hopefully you can gain a lot of insight by watching these tutorials, right? Anyways, let's get on with it. Let's start off with going through our specific requirements, right? So specific requirements is the material polypropylene, right? Or more importantly, PP. Then we had to have a max weight of 1,000, so you can go higher than that. Your chair base is pretty light, and if you have touched any chair base, you will understand that chair bases are not that light, right? So it's a pretty challenging task, but if you know the design considerations, then it's not too bad, which hopefully by this end of this tutorial you'll be able to understand everything. Then max wall thickness, or called the nominal wall thickness, which will probably be used in the rest of the video. Nominal wall thickness is here. This is the nominal wall thickness. You see this is your 5-spoke chair base, the bottom side. Nominal wall thickness, what is inside here is called a rib. This is a rib. This is also a rib, sorry. This is your nominal wall. This is your nominal wall, right? My apologies, right? So whatever's outside is called a nominal wall thickness, and your inside of your thickness should not be that thick, which is a mistake I made from a previous call, but I'll get onto that later. Anyways, what you need to know is that how to differentiate between them. Then a 50 diameter for your center hole, and 11 diameter and 25 depth, right? And 720 for the diameter chair base. Your diameter is not here. It's not this circle right here, right? This is only touching here. It's not the correct. You need to go from here, your tip end, to your tip end right here to be able to get the results you want, right? Only then it will be an accurate result. Oh, where's my thing? Okay, here. Then load usage requirements. This is for FEA analysis, and for 110 kilogram for 5 years, so approximately 120,000 cycles. So force distribution, the moment you see this, you will know force distribution is 110 newtons for all five of these chair pieces here, 5-spoke chair base. I don't remember what they're called. Yeah, or caster wheel. Yeah. So if pressures are distributed, right? So each leg will roughly have 220 newtons of force, right? And over here it says max stress level is 14 MPa, right? Megapascal. This value is gotten through an SN curve, which each material right here, right, polymer, polypropylene, has an SN curve. SN curve is basically stress to Newton, number of cycles towards stress, a graph, right, that shows that depending on the amount of cycle you have, the stress you will need to be able to tolerate that amount of cycles. And you could see from this graph, right, it says PP, which is polypropylene. This SN curve shows a number of fracture of cycles for 100,000, right? So 120,000. So you go a bit lower here, roughly around here, right? And you know that it's between the stress level of 20 and 10, right? So you want to go roughly around 15 and below. And my lecturer has said to be lower than 14. So each material has their own SN curve, and you need to understand. And as a designer, you need to, and manufacturer as well, you need to understand the individual materials and what you're using it for. Is it something that it's used a lot? If it's used a lot, then you need a more number of cycles. And if it's used less, right, then you need less number of cycles so it can tolerate more stress, right? This all have to do with engineering stuff, but you should still understand as a designer. All right, so let's get on to the model itself, right? Not model itself, sorry. Before getting onto the model, we need to understand injection molding itself. What is injection molding and how it works? Since we're working with PP, polypropylene, right? Polypropylene is obviously going to be injection molded, right? Injection molding, right, works like this. Right, you could see you have injector pins, you have your nozzle that shoots very hot liquid. This is your AB component. So A is where your nozzle is, and B is where your injector pins are, right? So AB parts are like here, okay? So when you are designing, right, you need to understand that you can't design a part that angles inwards, or else it can't be ejected, right? Or have overhangs, else it can't be injected, right? So that makes no sense, right? And also some design considerations are needed, like not being too thick, right? Being too thick, it will cause sink marks, because injection molding is a very quick process, right? And it cools off quickly. The liquid plastic cools off quickly because it injects liquid plastic into here, cools off quickly, and there will be a lot of issues, right, that you need to understand as a designer. And when you are designing, I have put on this link down into the description below, or I will, hopefully I don't forget, yeah, by this guy from 2025. It's official Solidworks blog that talks about the cardinal rules of designing injection molding plastic parts. These are the common knowledge you need to understand before designing, or before doing your CAD software modeling itself, right? First of all, over here it shows you, you should maintain a uniform wall thickness, right? Because non-uniform wall thickness like this, right, thick to thin, causes a lot of problems. Like this is just for sink marks, right? And then when you have sharp corners, right, the manufacturer, because injection molding, right, the AB part, right, it's created by a tooling or machinist, right? They will have to create this made out of steel or whatever, hard parts, right? They'll have to make all of this, and the more sharp corners you have, right, the easier it is to wear down. That's why for it to smoothly come off as an injection molding parts, you could see here rip flow design guidelines. You need to have at least of a 0.5 to 1.5 degrees, or a minimal of 0.5 degrees of draft. So let me just show you here, and hopefully you are able to understand this, right? You could see here there's a slightly little draft, right? You could see here there's a 0.5 draft around here, right? So all of this, right, all of this here to here, right, this is 0.5, right? 0.5 degrees. That is the minimum. Usually when we are doing manufacturing, we go for 1 just to be safe, right? Because sometimes you have texture, sometimes you don't have texture. This is for smooth surface. Smooth surface injection molding, 0.5, right? 0.5 degrees minimum, right? Rib height should be 2.5 to 3 times nominal wall thickness. You can't have it too high. If it's too high, it's gonna falter, right? You have a lot of issues, right? Thickness should be only 50% of 70%. We go with 50% of the nominal wall thickness. So you know nominal wall, or in this case, nominal wall is, let me just erase this. Nominal wall, this is your rib, right? And then your thickness here, rib here, this one should be 50%. And as you can see from this example, you can see here, this is my nominal wall thickness, is 2.4 millimeter, which is less than 5 mm, right? However, the issue is 2.79 for rib thickness. Oh no, what will happen? Sink marks. So this is a faulty mistake I've made that I forgot to change during my previous module, right? And hopefully you do not make the same mistake as me. Learn from my mistake and create a better outcome, right? And also another thing that I didn't do that well is, you know, uniform thickness. This is 2, just 2.4, not really uniform. Anyways, okay, so continuing, here is, where is it? Here. Other than rib thickness, you can see here, right, the height, rib thickness, fillet. As we talked about just now, right, any sharp corner means sharp steel, right? When they mold all of this, right, when they create these AB parts, right, they have a sharp corner, sharp steel. Anything that is sharp is easily chipped off, right? You do not want any sharp parts, right? You can just take something that I don't know, like a metal sheet, right? The more corner, the more surface area it has, the more it bends, then it snaps, right? Or a biscuit or something, right? So you need to have a fillet. This is very important, right? And base radii for this fillet should be 0.2 to 0.4 of nominal wall thickness. I recommend 0.25 lah, or 0.4. It doesn't really matter. Just 2.5 of nominal wall thickness, right? Follow this, right? And ribs should be, distance between ribs should be 2 to 3, because if you have ribs that are too close, easy to cause sink marks, right? That's it. So avoid sharp corners, recommended. See here, it's better to do this style, and even better to cut out a core section down here so that it have uniform thickness down. These are all, do not worry about all this if you don't really get it the first time. You will gain with experience. You will gain as you do. You will understand the more you do, and you can always ask your lecturer or always ask your supervisor for all of this understanding, right? There's actually a lot more than this, right? But let's just go for something simplistic. Yeah. So different type of plastics, right? So you have PP. So under Solidworks section here, you can see edit material. This is where you choose your material, right? I'll get on to this later, but importance is that you can see there are 2 types of PP. PP copolymer and PP homopolymer. Right? There are 2 very different material that has different uses, right? Right. They have different uses. What are they different? You need to understand the difference between a copolymer and homopolymer. If your lecturer has said you like to go for homopolymer, just go for it lah. But the difference between a PP copolymer and PP homopolymer is that a PP homopolymer is has more strength, right? But it is less flexible and more brittle, right? So it is able to withstand more force before snapping or bending than PP copolymer, right? PP homopolymer is also resistant to chemically resistant, also resistant to a bit of heat, more so than copolymer. So homopolymer is usually used in things like chemistry labs, medical equipment, cooking equipment, right? And outside, outside parts, plastic parts, right? They use homopolymer, right? Because although it is more brittle, it has more strength and more and resistant to chemicals and stuff like that. PP copolymer is the more general version of PPs, right? PP copolymer is more flexible, right? It flex more, right? This is important because when you're creating your 5-spoke chair base, you don't want it to be brittle. You don't want to have the moment it goes out of its S7 curve, stress level is just gonna snap, right? And create, or it won't snap directly. It will create micro fractures, which PP comopolymer is more less prone to happen, right? So for this tutorial, we'll be using PP copolymer as our standard guideline, but use whatever your lecturer has or whatever material that's suited for you, right? So PP copolymer, that is the difference, and you should understand them, right? Important. Now we have here, just change the material. I don't like this color. Okay. I want the material. Okay. So this is, and so for, yep. Okay. So before we end this tutorial, right? That is basically all you need to know, and the general rules. For the next series, we'll be talking about 3D molding, not 3D molding, 3D designing, CAD modeling, and design considerations. But before I end this tutorial, right, this introductory tutorial, I would like you guys to go try out and make your own chart base following these specific requirements. Where are the requirements here? These specification requirements on your own, right? So that we are able to test it out during the next tutorial session, right? So my chair base is very simple. It's just one extrusion, circular pattern, merge them together, then I shell them, get one part, because you can circular pattern one, right? Then have a core rib down the middle, right? Then you fill it. You fill it is because you do not want to have any sharp edges, like I've said, right? Sharp edges. Then you isolate this leg. Then you fill it again, whatever else you need, and you can always circular pattern down there. But you actually only need one leg because let me just go through this. Simulations only, there's something called cyclic symmetry in simulations, right? Which means it will simulate the entire thing as a circular pattern. I'll get more into that. Don't worry if you don't understand. You just need one leg, right? But it's better to have, to show this, because you need it for your module anyways, right? So anyways, for simulations, you need to go under one last thing lah. Simulations, you go under add-ins and activate your simulation under this tab here. Click here, or you can put it on startup, but it costs quite a lot, of memory. So just close it. Simulation, press OK, and in just a moment, bam, you will have a new tab right here called simulation, right? And this is where you create your new study and your simulation, right? Okay, that's it for today, and hopefully you guys enjoy this overview, and we'll get serious towards the next tutorial by modeling. Thank you and goodbye. Enjoy.